Yes, so if we are ready, I guess we can start the presentation. And today I'm going to talk about AiiDA Lab, which is the service that bridges the gap between experimentalists and theoretical scientists. So AiiDA Lab is already in development for quite a while. However, what we noticed recently that not many people are aware of what AiiDA Lab is actually doing, so what it is used for. And this is why we decided to basically bring to the public, also invite Carlo Pinelli from EMPA, who will be talking about how they apply AiiDA Lab at their daily scientific work. So the outline today is the following. We'll start with a quick motivation, how we design AiiDA Lab, what kind of tool it provides to us. Then I will show I will show the interface, how AiiDA Lab is working, and then there will be a 35-minute presentation by Carlo. He'll show how they use AiiDA Lab in their daily scientific work, and then I complete the presentation by introducing a few apps that can already be used for MOF community. So let's get started. Why do we need such a tool as AiiDA Lab? Of course, you might know that as a theoretical scientists, we quite often do high-throughput simulations. And the difference between running one or two simulations and running high-throughput is actually huge. The problem with that, when you run one and sometimes fail, you can just go to the supercomputer, check while it failed, and then basically fix the problem and run it again. This is not a problem. However, if you would like to run high-throughput simulations, you need to organize that system is stable enough that it can deal with the cases when, for example, machine gets shut down for some reason, and the workflow should be able to go there, understand that machine is not accessible anymore, and wait until the machine will become accessible again. So there are really many corner cases, and the case that I just described is actually not quite rare. So just recently we had a water leak that causes all CITES machine to shut down, so we had to deal with this, and all our simulation actually had trouble because of that. And this is only one case. Sometimes we have another problems. Geometry does not get converged, DFT does not get converged, and all these kind of things we need to deal with. So we need to provide a stable enough workflow that is able to deal with such corner cases. And this brings me to the second point. How do we design, how do we create such a workflow in an environment where many people can use them, and they can try to, they can profit from the community. If one person tries to develop a workflow that is robust enough, it will take years. If many people will figure out how to deal with different corner cases, that will already improve a lot and speed up the development process. Also, what's important that if we would like to share our knowledge, if we would like to share the results of our simulation, what we typically do, we make a report or we make a presentation. However, with AiiDA Lab, you can just provide some data. A person can directly go to AiiDA Lab account, see what are the output of those simulations, and see what the settings we used, etc., and basically understand what was done, what exactly was done, without need for people to interact. And then, so this brings me to a point where I want to discuss what kind of tools we allow, what kind of tools we use to make this possible. So first of all, we have AiiDA. AiiDA is a quite robust and complex infrastructure that allows to interact with different type of computers, with different type of code. So it provides interface that is unified, that can be used, and this interface can interact with different code and different computers. For example, you have different QA system, you have CP2K, Quantum Express, or whatever code you want, and AiiDA can deal with that. However, it's a bit complex to use. Therefore, we decided to provide AiiDA Lab interface, which kind of hides complexity and only leaves you with a few buttons that you need to click. You upload the structure, you click a button to get structure optimized, and then you have your results ready. So, and this, we think this is kind of a nice infrastructure to let also experimentalists enter the field. So they can also try to install application, run the simulation, and see the results, and use them for their convenience. So what kind of Well, what kind of user base do we envision? So first of all, there is computational scientists. Computational scientists, they typically quite familiar with Unix, Bash, or Python, so they can run high-throughput simulation by themselves, they can develop workflows, and they can develop AiiDA plugins. For them, it's typically just enough to have AiiDA installed. We typically work with command line, and we make plots with command line, we run simulation with command line, and this is perfectly fine. However, for many people, programming is not, I mean, they do not program in daily life, and it becomes complicated. And for them, we develop AiiDA Lab, which allows to, which simplifies a lot the creation of input files and submitting the calculation. And then there is a third case, which is kind of intermediate, students who haven't yet decided whether they want to be experimentalists or theoretical scientists, so they can install Quantum Mobile virtual image that already has AiiDA and AiiDA Lab installed. So you can just bring those tools, install it on your computer, and use it for your convenience. You don't need to have an account on in the cloud. Now, I will show you a quick demo just to give you an idea how AiiDA Lab is, how looks like. For this, let me just exit the screen. Yeah. Yeah. So this is a typical view how you get what you get when you log into AiiDA Lab. AiiDA Lab has this home application that is visually different from all the other applications that you have here. The point is that this application cannot be done. So what you can do, of course, if you would like to upload or machine file manager that is available here, you can just click on the button. Hopefully you can lit up. And here you have access to all the files that you store on AiiDA Lab server. Then you have terminal, standard Linux terminal. You have tasks. So if you would like to see what kind of tasks are currently running, you can just go to this page. And here you have a list of currently running applications. Then you have App Store that allows you to install applications that you want to use later on. For example, let's take a simple example. We would like to use a particular application. I don't know, we can choose anyone. So we want to compute persistence homology. We click on the install button, takes a few seconds, and then we reload the home page, and the application will appear as the first one among the installed applications. So this is persistent homology. I'll show you how you can use this application later when I give the second part of my presentation. Now I'll just give you a quick overview of what are the technologies behind, and then I leave the word for Carlo. So if you, when you log in with your AiiDA Lab account, you first of all get to Jupyter Hub, which is just authentication, which checks your username, password, and if it is correct, it allows you to enter the somehow confined environment that is only for you. It's called Docker container. You can think of it like a virtual machine that runs in this on the server. That is, you cannot access it from other people cannot access it, so it's only for you. And all this infrastructure is enabled by OpenStack at CSCS. Once installed, you can have access to any computer in the world where you can run your simulation. So first you get an account, then you configure a computer where you want to run your simulation, and this can be done anywhere in the world, even on your machine if it has publicly available IP. And then you're free to go with any code you want. It has plugins for AiiDA. So now I will leave the word for Carlo Pignatelli. So just a brief introduction. He obtained his PhD in physics at the University of Modena, and the work he was doing there was ab initio simulation of defects in gallium nitride. In 2003, he joined IBM Erushlikon, where he was doing a simulation of the electric properties of high dielectric constant materials. And in 2007, he joined EMPA, where he was doing simulation of surface-supported chemical reactions for graphene nanoribbons. And with this, I would like to leave the word for Carlo. Let's hope it works.
Good morning, everybody. Thank you very much, Sasha, for the introduction. I work at EMPA in a laboratory whose composition is mainly of experimentalists. And one of the main research fields in this laboratory at EMPA is, as Sasha said, the fabrication of graphene nanoribbons. So carbon-based nanomaterials that our experimentalists fabricate with a bottom-up strategy, starting from a molecular precursor that are designed and synthesized ad hoc by organic chemists. The idea is that to use these nanomaterials in the end to fabricate novel devices like field effect transistors. Now, why these nanomaterials? Why graphene nanoribbons? Well, I just tell you in 2 words, otherwise it would take too much time. Graphene is a material that is known for its excellent properties, not only electronic, but here we are focusing on electronic properties, extremely high mobility of charge carriers. But graphene has a problem. It does not have a band gap. So you cannot think about using pure graphene in devices where you need to switch off graphene. Now, a way to introduce a band gap in graphene, there are several ways, but one way is quantum confinement. You can imagine to cut graphene in one-dimensional stripes, and these that are then called graphene nanoribbons, and this will introduce a band gap in your material. Now, since to have a gap that is useful for information technology, you need to have stripes that have a width in the order of the nanometer. You cannot think of producing these materials with standard top-down approaches like lithography or cutting graphene. You need atomic precision in the fabrication of nanoribbons, because even a single atomic defect in such nanometric objects would completely destroy what are the theoretically predicted properties of the nanomaterial. And to achieve this atomic precision in the fabrication, several years ago, before 2010, in our laboratory, Roman Fasel and co-workers had the idea to follow the pioneering work from Leonard Grill. So start from clever molecular precursors that are deposited on a noble metal substrate. These building blocks will self-assemble into polymers and will then transform in the desired structure. Here I have 2 examples that are the earliest things on which we were working. This molecular precursor that was able to create just forming a polymer, just by self-assembling of this precursor, we were able to obtain a network of porous graphene. Or this was really the first system I was working on from the theoretical point of view, a molecular precursors for a nanographene. This was interesting because it was the simplest system with which we could study the intermolecular reaction, that is cyclodehydrogenation, that is the removal of the hydrogen and the forming of the carbon-carbon bonds here to go from this molecular precursor to this planar object. Applying these concepts to nanoribbons is straightforward, conceptually, not experimentally. And this is one of the first examples where our experimentalists succeeded. With these molecular precursors, they managed to obtain this kind of armchair nanoribbon. Now, this was released in the literature in 2010. Since then, the method appeared to be very reproducible and reliable, and this is just a snapshot of the wide family of nanostructure, well, in this case just nanoribbons, that can be obtained with the clever design of the molecular precursor. Not only different shape of nanoribbons, but also nanoribbons with a atomically precise doping, so insertion of heteroatoms substituting carbon. Now you can imagine that there is a huge effort from the chemical synthesis side to build up, to realize the molecular precursor. And after you have a molecular precursor, there is a huge effort, again, from the experimental side to manage to self-assemble these molecules and obtain the final product. Thus, it's quite desirable, before entering all these challenging efforts, to have some efficient way to predict the properties of these materials, to see if it's worth trying the attempt to have the molecular precursors and to have finally the ribbons. The pre-screening is nothing complex, just standard DFT to see if the band gap, the mobility of the carriers in these materials are in a window that are of interest for our goals in hypothetical applications. And you can imagine that also trying to understand what you have on a substrate while you are fabricating your object, the only tools that you have available from the experimental side are microscopy. Not always is easy from a microscopy experiment to understand what's going on in the growth chamber. And then it's quite useful to have simulations that reproduce the experiments of microscopy or spectroscopy to see if what the experimentalists are dealing with is really what they meant from the theoretical point of view. That's why after the demand for simulation in our laboratory increased a lot, we had to find a way to be efficient in providing promptly information on the electronic properties of these materials or on what is going on the substrate in terms of chemical reactions. Now, just to give you an example of how complex could be to understand what's going on chemically on a substrate, I picked up this example where our experimentalist asked for this molecule to the chemist in mind, and they had in mind to obtain this ribbon. They got the molecule, they started all the experiments for the self-assembly, but in the end they were able to obtain only this ribbon that luckily is also very interesting from the electronic properties point of view. Now, why is this happening? Well, the reason is that if you check what can happen on the substrate when you have the polymer is that the rotation of one of these fragments of polymer before the polymer transformed into an object is has an energy cost that is lower compared to the cleavage of bonds that you should have to have this kind of arrangement of the molecule instead of this one. This is just one step in studying the on-surface chemistry of these objects. For this particular case, the full picture would be this one, where every step of the reaction, for every step, we have an initial state, a final state, and a transition state. To obtain this kind of information, we need to run several simulations that are of the type of nudged elastic band. And just to give you an idea of what a nudged elastic band simulation is, I just have this pictorial representation. If I have a system in initial state and I know a final state that I want to reach, I can imagine to create copies of the system in between the path that is connecting the initial and the final state. I can imagine to connect these copies of the system with springs and then try to optimize this multidimensional object to achieve a path that is adhering to the closest minimum energy path that I had in my energy landscape. Unfortunately, if we deal with fully ab initio simulation for this kind of system, it's difficult to go beyond methods like NEB to characterize a transition state. And what is difficult in a NEB calculation is to create a clever guess for this initial path. So typically, a guess for the NEB path is a linear interpolation between the initial state and the final state, but you can easily imagine that if I am dealing with the rotation of a segment, I cannot do a linear interpolation because otherwise I would just have intermediate configuration where the atomic configuration does not make sense. Now, all of this, of course, I come from a traditional way of doing simulation. For my standard way of working was kind of having a lot of windows open on my screen, checking the status of calculation on a supercomputer, editing an input file for CP2K or Quantum Espresso, checking output files and checking geometries. Now this is a little bit inefficient, and we try to move to something that could be used efficiently in collaboration with experimentalists. Now, we have to imagine that from the computational point of view, our work in this field starts in a way like this. So we get this kind of information from the experimentalist. We have this molecule, we measured, we obtained these images. We would like to see what these STM images really correspond to. And what we want to obtain is a ribbon that has this shape. Can you simulate it? And then our idea was to take advantage of what was developed in AiiDA and what would have been developed in AiiDA lab. And we started writing a work chain for nanoribbon characterization. The work was started by Sasha before the AiiDA lab thing. And we really designed every step of this work chain in collaboration with the experimentalists because we wanted for this to make them able to run this kind of simulation. So everything starts, now I have to apologize because I have a series of movies. I know it's boring, but it's the only way I found to be efficient in this. So they start typically with the chemical sketch that they store on the computer. And this chemical sketch has now to be transformed into a periodic unit cell on which I can do a quantum espresso simulation. Keep in mind that our experimentalists, many experimentalists, I also, love to use standard chemical software for chemical drawings, and typically you don't know what are the length scale that you get in your drawing of the structure. So we said, okay, first step is that I want to upload a structure that I obtained from a chemical drawing tool, and after I upload it, I have to check if the scale of the structure is matching the standard carbon-carbon distance that I have to have in a simulation. And this is what is done here. After uploading, I do a check where I select my just uploaded structure. The interface will suggest me a scaling factor. I'm fine with it. It's applied, and I store the new structure. Next step is construct a unit cell out of the structure that I uploaded. And since in the experiment, the nanoribbons that we have have always a hydrogen termination at the edges, we decided also to make it easier for the experimentalists to use this interface to automatically hydrogenate the structure that they were getting. Now here I just have to select two equivalent atoms in my structure to define a unit cell, and in this case that's shown here, I will define a supercell because maybe I had in mind afterwards to have a doping in this structure. I'm fine with this, I construct the unit cell, and automatically I get the hydrogens added to my structure. If I'm fine with the structure, I can save it with a name that is maybe shorter than the one suggested automatically by the application. And unfortunately, I cannot speed it up. I'm sorry for this. And the next step would be to modify the structure, because, for example, a typical thing that happens in the experiments is that they can have edges that are not singly hydrogenated, but have a double hydrogenation. And then we decided to easily add this feature. And maybe it could be interesting to replace, to add spin. So here we say that we want a spin polarized calculation, and we say that for the initial guess, this has to be a spin-up configuration, and maybe we can also insert a dopant atom replacing a carbon. If we are fine with the structure, again, we can store in AiiDA. And now we are ready to submit the calculation. What we will do now, we just retrieve one of the structures that we are ready from our database. I will not pick up the one modified, just by mistake. I select one of the many available computers that I can have. Just before Christmas, I had 10 logins active. And I submit now the full work chain of calculation that will compute band structure, will compute Kohn-Sham orbitals, will compute projected density of states. Now, this is the first part of making life easy. The next part is, let's see the results. After the calculation is completed, the results are automatically stored in a database that I can query with an interface that we are at present modifying. In the example here, I just set a range of values for the possible absolute magnetization of the structures. I search for the structures that are compatible with this, and I obtain the results. Here I can check these boxes to compare the band structure of the checked structures, or I can go to these more detailed views where, for example, I can see the band structure of my ribbon, together with, now I can click on a band and follow the evolution of the orbitals along this band. This is information that is extremely useful to quickly understand some features in scanning tunneling spectroscopy experiments. And here I was changing a point, and here I have also the map of the spin density. And for ribbons that are newly computed, we can have this also as an isosurface in 3D. Another example here, I want to identify features that are coming from a specific atom. I can select the atoms that I'm interested in, for example, the atoms in these units, Atulin units. And then I can plot a density of state of the system together to the density of states projected on the selected atoms. This is, and here we have this, and we can also export this image in several formats, as an image or also as a raw data, PDF, and here is missing the raw data that can be edited then from the experimentalists. Now, is this useful for what we had in mind before? Now, keep in mind that here we are addressing what are repetitive tasks that do not contain anything really new from the computational point of view, but that are really kind of a bottleneck to our routine work if we are slow in doing these repetitive tasks and if we do the standard errors, mistakes that we have in these tasks. Now, I work with Roman Fasel since more than 10 years, and he got used to the fact that I am a messy person and sometimes not always efficient. And at the beginning, the standard conversation with us, between us for nanoribbon was, some while ago, I told you about these ribbons. Did you compute the band structure? If yes, do you have them available that we should check them? And this while ago can be easily 1 year ago. And for me, to retrieve calculation that I did 1 year ago was always kind of not easy, and I was typically redoing the calculation. Now, this is kind of solved, and I just bring you an example from our lab. This is Chan Soon, is an experimentalist. He's an experimentalist PhD, just a weekend in the lab. He was doing these measurements, experiments by STM. This is really a snapshot of one of his slides presented on a Monday lab meeting. And the next slide was DFT calculation by AiiDA. He did the calculation, and he's considering AiiDA as a tool at the same level as the STM. I had to do nothing to do these results. And how our conversations evolved recently. On a Thursday evening, Roman doesn't write to me anymore. He writes directly to the experimentalist and says, we have band structure for the last two. So I'm discussing priorities with another experimentalist. We have this band structure. Could the missing one be done quickly? And he also includes in his email the AiiDA results that he claims we have. And when I realized that Roman wrote the email, Chan already replied, I will run AiiDA DFT. So this is, to a large extent, making my life easier. I don't have to waste time anymore frequently on routine tasks. This is just an example for nanoribbons. Now, if we want to go on the surface, we want to do real spectroscopy and microscopy or understanding the chemistry on the substrate, we have to go from this object to this object. And we want to do it easily again. Now, not because I want to empower experimentalists to do it, because otherwise I lose my job, and also because I don't want to give them access to challenging, too expensive calculation on a supercomputer. So for the moment, this I'm still doing alone, then we will see in the future. This image, just to keep you in mind that if I have to, since typically I have to optimize the geometry of objects that are basically physisorbed on a gold or copper or silver substrate, it could be a clever step to have a refinement of the structure with a cheap method. That is, we treat the molecule with DFT, the substrate with kind of an embedded atom model, and we plug in between the two systems an empirical force field that is mimicking the van der Waals attraction. So we also, in designing the app that I will show you afterwards, we also added the possibility to run this fast kind of calculation to refine a structure and then do the full DFT on these objects that are typically in the order of 1,000 atoms. Now, starting step, let's build up a slab, a gold slab. Did I push it? Yes. Starting from a molecule that is in a database. We pick up an uploaded molecule. Again, I have to apologize, it's a little bit slow. And I will probably pick up this one if I remember well. Then I automatically get a guess for the slab. I think it's too small. Then I increase the size of the slab. And here I'm taking coordinates that are kind of already pre-relaxed to speed up things. I want to rotate my molecule. I am fine with the structure. I just have maybe to find a nice name. I did not do it, and then I store it in AiiDA. And now I'm ready for running a calculation that is a geometry optimization, sorry. And here, as I said, I have the possibility to decide at which level of theory doing this geometry optimization. I select my edited structure because I created the slab. This is another one. I select the computer on which I want to run the simulation. I get an automatic guess of the parameters to put here, so which atoms to keep fixed, how many nodes I should use. I get a summary of the analysis of the structure. We are going to make this more general, so valid not only for slabs. I check that the structure is the one I have in mind. I check that I'm fixing the proper number of atoms. The guess was done automatically, is fine. I select which level of theory I want. I don't want to do an hybrid calculation. I will do just full DFT with dispersion correction. I find out a name that hopefully I will remember, and I submit my calculation. Now, the work chain will take care to resubmit the calculation till it is converged. So typically, of course, a single calculation goes beyond the 24 hours, and it could be resubmitted to 5 times. The next step is to look what I have in the database. And it is making really our life much, much easier. Again, I have a search interface where I can specify keywords or chemical formula. We still have some bugs here that we have to fix. And I will get, as for the nanoribbons, here a list of structures that were already computed, and there will be active links for properties that have been computed. For example, density of states, STM images, or down, 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 not only gold, this is palladium, gallium, atomic force. So if you compute more than one set of STM, you will have all of them listed. And we have also AFM images, down, 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 down. It was a while ago that we did the last one, well, in October. Let's have a look to what happens if we go on the PDOS link. This is extremely useful to identify where in my calculation I can find the features that experimentalists see in scanning tunnel spectroscopy. Here I get 2 selections. Here I can select which portion of a molecule I defined for the projected density of state to be visualized, and I can select on which color. In this selection, instead I have the contribution of the gas phase orbitals of the molecule onto the full set of orbitals of the system. So I basically compute in gas phase the orbitals of the molecule, and I do a scalar product because between these orbitals and the orbitals that I have in the full systems to see if the features of the molecule in gas phase are intact on the substrate, for example. And then once you are fine with the colors and the filling options. And the big success here is that we defined a standard that is okay also for our experimentalists, so the image that we have here is ready to be put in a presentation or in a manuscript. You don't have to edit it anymore. Then you plot it, and you get right on the right the scale bar for the projection of frontier orbitals, and this instead is the standard projection on atomic orbitals. And this kind of plot can be visualized or modified anytime because everything is automatically stored on the AiiDA database. And these plots are done on the fly on the virtual machine at CSCS. Next thing is how to create such a PDOS calculation. So once I have a geometry optimization done, I can select the optimized geometry a little bit back in the past. This I could have maybe cut. I want to search between calculated structure that belong to this work chain. And I pick up a copolymer, so this is a huge calculation, and I want to define regions of this molecule where I will compute the PDOS. And then I say I want first this selection. I check that is what I have in mind. Yes, it's a portion of heptacene. And then I have this other selection that is an azulene unit in the backbone of this indenofluorine. If I'm fine with both selections, let's check if I picked up the correct azulene units. That's what I had in mind. And then I say that I will also want 4 filled and 4 empty orbitals from the gas phase, and I can submit the calculation, and the result will be this link that we had in the structure browser. The same way one can submit and retrieve STM simulations. We just did the STM simulation for this structure, and then we can retrieve all the STM and STS simulation done at different, let's say, bias voltage, either at specific points in energy or with the constant spacing in a range between -2 and +2 electron volt. I decide which series I want to visualize. I want this STM, for example, and then I want also this constant 8 STS. I'm fine with it, and then I ask to plot the results, and I will get this slider, and then I can compare which one of the computed features is matching the experiment, and then I can understand where it's coming from, a specific feature in the experiments. And of course, also all these things can be organized in a zip file and downloaded with a link that is hidden below here. Now to go to reactions. As I told you, a delicate thing is to create the initial guess of an EPFL calculation. In this case, I show you the example of a CH2 molecule, acetylene, that is rotating on a palladium gallium substrate. This is probably the smallest molecular engine that will be ever demonstrated if our experimentalist will manage to complete submission of this manuscript. And I pick up the geometry optimized for this molecule on palladium gallium. And what I want to do, I want to create intermediate images for this molecule to rotate by 60 degrees. And then I have to define, look, here I can retrieve the index of this atom, the index of the atom. I want to define a collective variable that is the angle between the bond, carbon-carbon bond, and the given direction. I select the computer, number of nodes, name of the calculation. Again, I already have the guess. I have to increase the cutoff because it's palladium gallium. And then I want this kind of collective variable. These are according to the definition of CP2K. I take atom 565, atom 566, that are the 2 carbon-carbon atoms as I found. And then a fixed point to identify the y-axis. Here I made a mistake when I did the movie, because I did not click fixed point. So you will not see visualized the y-axis. And then I can define intermediate values for my images. To define this, let's check what is the actual value of the collective variable. I picked up the correct atoms, and the initial value of the collective variable is 64. And then I will ask the work chain to create all the images in between 70, 75, and so on. And this calculation will run only after this one is completed, because I want to smoothly see how the system naturally evolves from an initial state to a final state that I have in mind. And this is a way to create a guess when you don't have an easy way to create a guess for an EPFL. Now you submit the calculation, and you can visualize the outcome with an app. that will retrieve, also if you decide at a certain point to continue this series of calculations, this app will automatically detect that you were continuing a replica chain calculation, and you get all of them. You have the profile energy, you have the list of all the intermediate structures that were optimizing, obeying to the imposed constraints. So this was the target constraint, this is the effective one obtained. I can export every single structure. I have a list of all the structures that were computed. I can decide that I don't want this one, will be removed to the list. No, I want it, will be added. Then if I cut and paste these PKs in the interface to run a NEB calculation, then I immediately can run an algebraic elastic band calculation. And the next step is just instead to visualize a NEB calculation. Submission is straightforward, I don't show you. And I take the case of the rotation of this unit of the Pirene ribbon. So this is the NEB calculation done with 35 replicas. This is a plot to check if it is converged or not. And here you have the structure, and then you can move this slider to see how is evolving the NEB along your path. Here again you have all the list of structures along the nudged elastic band path. You can export every single one, and you can check what was going on just from this viewer. Here I was not smart enough to make a nice transition. And this again is making easy what was in this case a really tedious routine work. Of course, I'm still speaking about routine work. And this is just the interface that I show you how to submit an NEB calculation. You just again can decide the level of theory, and here you just plug the PKs of the replicas that you want to use. And here there's a nice thing. You can retrieve the wave function for replicas that were already computed if they are still available. And this has speed up the calculation in its initial steps. Now, if I think I have still 3 minutes. I just want to show you. So this is how AiiDA Lab shows itself to a user. If you want to modify or to create something, you have to abandon this app mode and edit the application. And then you will see that the code is just Python. Is a little bit bulky in the first version we had for all these apps, but then we moved towards the concept that Sasha and Leopold showed me, the concept of the widgets. And what we are doing now for one of the apps, trying to define widgets, we have that everything is as short as this. We have some control function, and this is just all the widgets. This is just the page of code that I have to have for having all these selection widgets. Just it. So the main part is just the import part. And this makes much easier to develop new apps, to cut and paste parts from one app to another, and to check if you have, well, to avoid making errors when you're doing new apps. What is difficult in here is to define widgets that can really have a general purpose. This is one thing that I want to discuss with the AiiDA developers, to find strategies, efficient strategies, to have widgets that are not only really for a specific use, but can be used for many other applications. This is what we are trying to do, to rewrite a little bit our apps and try to define new widgets. There are, of course, problems. The problem that we personally mainly encounter is that if you start having huge databases with structures that have a lot of atoms, the query builder is a little bit slow. And I'm sure that this is a problem that can be fixed. And of course, seeing how, from our side, our database is fastly growing, we hope that there will be investments in the infrastructure in the future, because at some point we will need a really powerful infrastructure. It's mandatory acknowledgements to all the people in the AiiDA business. Especially you have to thank, of course, everything started with Sasha, as I said, Leopold, Ole, of course. Ole was initiating the AiiDA Lab project. We have to thank Giovanni Pizzi, because he was extremely patient in supporting us at the beginning and understanding all the AiiDA world. Christian Emre and Edward Dietlet wrote a lot of also these applications. And of course, even if I didn't show any science, all the science that is behind this, behind the nanoribbons, I must acknowledge all the groups involved at EMPA and all over the world and the financing agencies. That's all I wanted to show you. Thank you very much. And whatever question you have, I'm available also in the future.